Okay, so I'm Alan Davis, and I'm presenting as lead for the Clapeyron experiment. So we're going to start off with, we're going to go through the scientific goals and what we actually want to accomplish through this, and then from there we will go through how the experiment actually goes, and then what our data means and how we can actually use it. So for background, the Clapeyron equation governs the relation between saturation pressure and temperature, between enthalpy or latent heat of vaporization and the change of phase, and it also shows the specific volumes in different phases. So we can use temperature and pressure to find enthalpy or latent heat of vaporization for a substance, in this case water. So the actual equation is here with the change in saturation pressure over change in temperature equaling the latent heat of vaporization over the temperature times specific volume. So this can be simplified using ideal gas equation because it's not super compressed or anything, it behaves as an ideal gas. So using that, we can take out the specific volume entirely and just have the latent heat of vaporization, saturation pressure, temperature. So what we're looking at with the phase changes is when it's becoming a saturated vapor. So it's on the line between your vapor and your liquid phase here, below the critical point. Because at that point, you get into a supercritical fluid, which is not what you're dealing with here. So the scientific goals of this is to determine the latent heat of vaporization of water using the Clapeyron equation. The experiment should verify known values that we have from thermodynamic tables using the temperature and pressures that we're going to find through this experiment. So the apparatus that we have is we have a flask here, a thermocouple here, which has already been described from the reports the last time to measure the temperature, and we'll also be measuring the pressure here, which, from what we've shown, is you through send vapor here, you get an air bleed valve here, and a vacuum control valve from the pump right here, which will create a very low pressure, and the water reservoir. So the procedure we're going to need to do is we're going to have to verify the functionality, configuration of the data acquisition, which is using an Omega system, which the computer should already have. We'll add water to the flask and the reservoir until sufficient levels are reached. Check the system for leaks by closing the bleed valve, and we'll drop the pressure down with the pump, turn the pump off, see if there's any leaks. It should stay almost at a vacuum, like it started after a little while if it's actually sealed. So then we'll open the control valve, turn on the hot plate, and when the beaker reaches a boil, start taking data, and slowly close off the line of the pump, just keeping it at that sealed low pressure. So to shut the entire procedure down, we'll open the bleed valve, close the vacuum control, and then shut down the pump, the heating plate, and finally the power. Some important notes when running the experiment is going to be, make sure you read through all the instructions before. This doesn't include everything, and you need to know how to run it, obviously, before you start. The thermocouple should only be in contact with the water because the heat transfer is different through water or liquid as opposed to if it's touching the sides of the beaker or the bottom or it's in the air. And before the pressure reaches atmospheric pressure, when the boil, open the air bleed valve to avoid pressure from building up. That's kind of the release. And should note the pressure and temperature at atmospheric pressure as a calibration check. It should be just the same as it is, around us now. So that's a good baseline for calibration. And clean up after yourselves. Obviously, follow safety rules. So expected results This is a typical saturation vapor pressure over water surface with temperature. So we should get something that matches something similar to this. Obviously, we'll be dealing with the ranges between room temperature around here going up to boiling. And these will also be used to calculate the latent heat of vaporization. And for the data analysis, we can show the derivation here by multiplying by Pt divided by pressure, in which this is how we would calculate the latent heat of vaporization for different temperatures. So, appendices, I brought a thermo book with a lot of steam tables in the back of it. Got the instructions and another table here. So this is how we can verify using previous equations whether we're getting numbers that make sense or not. Any questions?